Okay, hey guys, can you see me and hear me and see my slides?
Yes.
Okay, great, wonderful. I've got a couple of things to get everybody's brains warmed up while folks are still joining and getting checked into the class. So go ahead and take a moment to take a look at that, and then we'll talk through them together in just a second. Okay, so hopefully you guys all have been practicing your Lewis structures like we talked about last class. I just want to take a moment and kind of have everybody get warmed up a little bit. So let's go ahead and figure out together how many total valence electrons are in each of these systems. So I gave you guys a little bit of the periodic table to use while you're figuring this out. But remember, most of the time I won't be able to devote slide space to that, so you guys will have to refer to your own. So let's go ahead and get started. For the molecule on the left, has anyone figured out the number of valence electrons?
Yeah, 20.
20, great. So the easiest way to do this is to break down into each element and how many each element brings in. Hydrogens, can you guys all make sure you're muted, please, if you're not answering? Thank you. There's 6 hydrogens, and so each brings in 1 electron. There's 2 carbons, which each brings in 4, so we'll get 8 total electrons from carbon, and we'll get the 6 valence electrons from that 1 oxygen. This is an overall neutral molecule, so we are all set and done, and that's our answer is 20 electrons, 6 plus 8 plus 6. What about for the molecule on the right?
29.
30.
I heard a 29. Anybody have a different suggestion? I see a 28. So let's work through this together. How many hydrogens in the system?
5.
5. So you're gonna have 5 electrons from the hydrogen. How many total carbons in the system? So 3 carbons and 4 electrons each.
12.
And can you guys mute your microphones, please? I'm looking for my power button. Okay, thank you. All right, so we're gonna have 12 electrons coming from the carbons. So it's 3 carbons with 4 valence electrons each, and another 12 coming from the oxygen. So that's another 12 because it's 6 electrons for each oxygen and 2 oxygens. So now 5 plus 12 plus 12 makes 29 total. But we have to account for this. What is this? This is a positive charge, which means this C3H5O2 plus is not a neutral molecule. So we just counted that these atoms, if they were just, their own atoms, they would together make up 29 valence electrons. But with this positive charge on the overall molecule, we know that in order to get a positive charge, we have to remove one of those electrons. So the correct answer here is 28. And here's the breakdown for how you get that. 5 plus 12 plus 12 is 29. And then because we have a positive charge, we have to remove or subtract 1 electron. And so that's gonna be 28 total electrons. Okay, so hopefully that kind of got everybody back in the groove and refreshing your memories from last time. And we're gonna go ahead and forge ahead here. I just have one reminder, and that's that I have office hours. I told you guys I would begin these office hours today, and indeed I'm going to. So I will be in the Zoom link for office hours. It is not this Zoom link. It's the Zoom link that you can find on your syllabus on Canvas. So I'll be there from 3 to 4 today. And today in particular, I have to leave right at 4, but I might, on other days, I might be able to stretch that out a little past 4, but today I'm gonna have to jam right at 4 for another meeting. Other announcements. I did post an Achieve Chapter 1 homework. You guys can see that on your Achieve page. It is due Monday morning at 9 a.m. So my goal here is to make sure that you guys have it due before class. but I didn't want to not give you kind of the whole night before. I don't know about you guys, but sometimes I work past midnight, and so, you know, an 11:59 p.m. deadline doesn't really need to be set if we're not meeting together until 1 p.m. So this is a deadline, 9 a.m. I'm going to keep all of the Achieve assignments due at 9 a.m. for the course of the semester. Someone's asked if the homework is always due on Mondays. It is not always going to be due on Monday. It will always be due after we finish the chapter. So if we are, you know, not making it through timing wise to get through the whole chapter, then I will push back the homework due date so that we have the whole chapter covered before it's due. Okay, on that same note, don't forget to do the Getting to Know Achieve extra credit. You can find this in Achieve. I'm going to extend the deadline on that until this Friday. So just make sure you do it. You can still do it after the deadline. It'll just be partial credit instead of full credit. I did a poll in my last class, and about 80% of the class thought it was really helpful. So go ahead and do that. I think it'll be beneficial for you. Just one more note about Achieve, and that is that all of the assignments for Achieve and all of the grading for Achieve, I'm going to keep separate and localized in the Achieve interface on Macmillan's website. So I will create a dummy assignment within Canvas so that it puts a calendar entry in for you guys within your Canvas to help you keep track of deadlines. But there's not, aside from that, there's not going to be any interfacing of Achieve and Canvas. I tried to do this in the past and it really mucked up my grade book, and so I'm not doing it that way. So if you do an assignment in Achieve, or if you want to check on your grades in Achieve, you have to go to the Achieve site. At the midterm and periodically throughout the semester, I'll post your current Achieve score into Canvas so that you can do all of that, like, you know, self-calculating grade stuff that you guys can do in Canvas. But for the most part, I won't be converting individual assignments over to Canvas. Okay, finally, if you were not here on Monday, just a reminder to be sure to complete and upload the in-class participation activity to get Herschel credit. And you can check out the slides posted from Monday's class. I have not yet gone through and graded the rest of them, but I'll hopefully get to that before Friday. But you guys who didn't do it and want credit for this, make sure you do it ASAP, because if you don't upload yours before I upload the answer key, then you'll get some partial credit, but like way less, okay? Any questions? If there's no questions, please make sure your mics are muted. All right, here is the outline for the chapter. Today, we're going to hopefully get through another nice chunk and be more than halfway done before the end of the day today. This is the chunk that we're going to go through today, beginning with formal charges. Last time in the last class, we finished with Lewis structures. They'll keep coming up again and again, so make sure you guys are practicing those. Today, we're gonna start on formal charges, and you'll see what I mean by that as we go through. All right. These formal charges are a human tool. They're just like Lewis structures are a human tool that we as chemists came up with to help understand and communicate with each other about where electrons are in a molecule. Formal charges are another tool for that same thing. They may or may not correspond to actual charges or charge density in the molecule. Don't worry too much about that statement. Just know that formal charges are a very black and white, very specific thing, and I'll show you right now how to calculate them. An important point here is that a complete Lewis structure, if I ask you to draw the Lewis structure, a complete Lewis structure will include an indication of all formal charges in a molecule that are not equal to 0. So a formal charge is a charge, either a positive one or a negative one in some quantity, so +1, +2, -1, -2, or 0, that is associated with an individual atom within a larger molecule. And you'll see that become clear as we see some examples. This is the equation that the book uses to calculate formal charge. So this is where I'm going to start with you guys and explain this equation to you. And after we go through this and do some examples, I'll show you a couple of other ways to think about it. So what we're going to do is go through this one by one with some examples to make it easier. Here are the examples. I've given you the molecular formula for H3O plus and for NO plus. And I've drawn out Lewis structures that include all the electrons. So I'm showing you all of the electrons on these Lewis structures, but I have not put in formal charges yet. So we're going to go through together and figure out the formal charge on the oxygen atom here. And we're going to apply this equation. So in order to do that, first we figure out the group number. So what's the group number of oxygen?
6.
6, thank you. All right, so we've got a group number of 6, and then we have to subtract the number of non-bonding electrons. Non-bonding electrons are exactly what they sound like. They're electrons that are not part of bonds. So in the case of this oxygen atom, it has 2. They're hanging out together as a lone pair, but even though it's a lone pair, it's 2 electrons, right? So we take our 6, we're going to subtract 2, that gets us down to 4. And then from 4, we're going to count up all of the shared electrons that oxygen atom is claiming that are shared with other atoms. We're going to divide that number by half. So this oxygen is sharing electrons with a hydrogen here, and one here, and one here. So it is sharing 6 electrons. And so half of 6 is 3. Now we have 6 minus 2 minus 3, which gives us 1. Okay, yeah. So we've got 6 minus 2 and minus half of 6. That 6 here in the parentheses refers to the 6 electrons that are in the bonds, whereas this 6 here refers to the group number. So if we do that math, we get 1, and indeed, the formal charge on that oxygen atom is plus 1. So you'll see the formal charge signal here is a little plus or a little minus, or a plus in a number or a minus in a number. Sometimes they'll be circled, sometimes they won't. All of these are acceptable. The important thing is to be clear about which atom it's associated with. And so you just need to make sure that it shows up like closest to that atom that it's associated with, so that nobody could, think it was associated with a different atom.
I have a question.
Yeah?
So does formal charges not apply to hydrogen?
Okay, so that's a good question. Hydrogen can have a formal charge the same way that any other atom have. It just usually doesn't. Okay, so if I ask you guys, make sure to show all of the formal charges in the molecule. You don't really ever have to worry about hydrogen as long as it looks like it does here, where it's kind of like a hydrogen with one bond to one other thing. If you work out the equation, hydrogen is group number 1. It has no non-bonding electrons, so it's 1 minus 0 minus half of the 2 electrons that are in the shared bond. So it's 1 minus 0 minus 1, which would equal 0. So hydrogen has a formal charge here. It's just that charge is equal to 0. Does that make sense? If you have H minus, like the hydride anion, which you guys will learn about later in this course, you don't have to worry about it now. That's a hydrogen atom that carries 2 electrons, and that has a formal charge of minus 1. So there are exceptions. All right, someone in the chat box has asked, are non-bonding electrons the same as core electrons? And the answer is no. What core electrons refers to is electrons that are very close to the nucleus. So this oxygen atom has 2 electrons in the 1s orbital that are not part of its valence shell. The core electrons are the electrons underneath the valence shell. And for all of the Lewis structure drawing and formal charges and resonance, which we'll talk about next, and for most of organic chemistry, you only care about the electrons in the valence shell. And so the core electrons you can just kind of ignore for now, but you need to remember they're there. Someone else has asked, does it matter what side of the atom the plus is supposed to be? No, it doesn't matter as long as it's clear which atom it's associated with. Is the group number 6 because that is how many valence electrons oxygen has? Yes, that is true. It is also group number 6 because it is in column 6A of the periodic table. Man, my lights went out early today. Hold on, guys. Okay, and do we only use the group number from the central atom? Is the last question in the chat box right now. So you use the group number from the atom in question. So remember, Formal charges here are associated with a particular atom within a molecule. So it's the group number of whatever atom you're talking about. Someone else has asked, where did you get 2 from? 2 in this is the number of non-bonding electrons on oxygen. And I'm going to hold off on more chat questions for now, because I think you guys will see the answers to your questions over the next couple of examples. So hold on to your questions until we get through another example. All right, so for NO over here, according to this Lewis structure, we can assign a formal charge where we can calculate what the formal charge is for nitrogen and for oxygen. So let's start with oxygen. We're still in group number 6. How many non-bonding electrons we have? So we have 2 electrons that are associated with this oxygen that are not part of a bond. And then we have 6 electrons that are being shared. So we'll have to take half of 6 again. So the math turns out to be the same as last time. So it's the same exact equation. The rationale is a little bit different because here our 6 shared electrons are in a triple bond with the nitrogen, whereas over here our 6 electrons were in 3 single bonds. But it doesn't matter, they are still all shared electrons. We're not going to differentiate them. And so what we are going to do is count them all up, divide by 2. So 6 minus 2 minus 3 is plus 1. And there's that plus charge. So now you can see over here it's up and to the left, over here it's down and to the right. It doesn't matter where it is as long as it's clear which atom it goes with. For nitrogen, we go through the same process. For nitrogen, it's a group of 5. It has 2 non-bonding electrons that are over here in this lone pair. And then of course it also has the same 6 shared electrons, so we have to take half of 6. In the case of nitrogen though, 5 minus 2 minus 3 is 0, and nitrogen does not have a formal charge. So now that we've assigned all of our formal charges, we can say that these Lewis structures are now complete. Does that make sense to everybody? We'll see some more examples and you guys will get to practice. So I'm going to keep going unless I see messages pop up in the chat or you guys jump in. Okay. Formal charges are localized on individual atoms, but I want to make sure everybody understands that you might have these formal charges on atoms within a molecule, even if the overall molecule is neutral, right? So all of the formal charges have to add up to whatever the overall charge is on the molecule, but you can have charges on individual atoms. All right, someone has asked, well, we always have to do separate math like for N and O, and you separated the math while the H3 and the other didn't. Okay, so again, these formal charges are going to be associated. You have to apply the equation for each atom within a molecule. So in the case over here, we went through the equation for oxygen and nitrogen and oxygen, and each of those equations is written out here. I verbally went through the equation for one of these hydrogens to demonstrate to you guys that the formal charge is equal to 0. Whenever you see a hydrogen just bonded to one thing, that formal charge will always be 0. And that's going to be the most common way we see hydrogen. So most of the time, we're just going to ignore the hydrogen. If I'm asking you about these sorts of things on a test, I will say to you, make sure you draw in all of the formal charges in the molecule that are not 0. Or what is the formal charge on the nitrogen in this molecule? Those sorts of things. Make sense? Okay, so let's try it together on our own. I want you guys to determine the formal charge on each atom in H3NBH3. And the very first thing you have to do is draw the Lewis structure. So now I don't have the rules for drawing the Lewis structure up for you guys because you won't have those rules on tests or quizzes. So that 1, 2, 3 set of rules, but hopefully you guys have done enough practice that you can go through it and do it on your own. So go ahead and take a minute and draw out the Lewis structure of NH3BH3.
Boron is from group 3, correct?
Could you say it again? I couldn't hear you.
I just wanted to confirm. So boron is from group 3?
Yeah, boron is from group 3. That's right.
Okay.
Once you have the Lewis structure drawn, go ahead and apply the equation at the bottom so that you can get the formal charge for, of course, the most important ones to do are the ones that are not hydrogen. So start with nitrogen and boron. And then once you've done nitrogen and boron, you can think about whether or not you need to worry about the hydrogen atoms. I'll give you guys another minute to get through this and then we'll talk it through. Okay, let's go through this together. This isn't for upload or anything like that, so we're just gonna go through it together. To do the Lewis structure, we would have added up all of the valence electrons, how many valence electrons there are in the whole system. How many did you guys come up with? Should have 5?
14. 14.
Great, 14 is right. We've got 5 coming from nitrogen, 3 from boron, so that makes 8, and then plus another 6 from all the hydrogen atoms. So here is how you can arrange those 14 to try to satisfy the octet as much as possible. I gave you guys a hint about how to organize your atoms. So here is the Lewis dot structure. Hopefully you guys drew it as a regular Lewis structure with lines instead of dots, because that's what I prefer. But this is the picture your book gave, so this is the one we're going to use. So you can see that nitrogen has 4 bonds and no lone pairs, and same thing for boron, right? So that means that each of these atoms, nitrogen and boron, has 8 bonding electrons and no non-bonding electrons. So the only thing we need to know now is the group number for each, which we already knew from calculating Lewis structure. So for the case of nitrogen, we've got 5, group number 5, minus 0 non-bonding, minus 4, which is again half of the bonding electrons, right? For boron, oh, and that makes +1, and you can see that plus sign right here. And you can go through the same math for boron and get -1, and so you can see that minus sign here. So hopefully that's making sense to you guys. I just want to take a moment to point out that 4 bonds gives you 8 bonding electrons, right? When you take 8 bonding electrons and divide it by 2, you get the number 4, which is the same number as the number of bonds. So it might have seemed like some circular random rambling from me, but the reason that I was saying it is because that'll play into some of the other ways to think about formal charge. This is the equation that your book uses, written down at the bottom here. I won't give you this equation on an exam. I find this equation to be not very intuitive, so I'm going to tell you guys another couple of ways to think about this. They are all functionally equivalent. They will give you the same math to get you to the same place, and they are all correct. So you just need to figure out whichever one makes the most sense to you personally and apply that one. So here we go. Again, this is the equation that your book gives you. Another way to think about this same equation is that instead of the group number, you can think about the number of valence electrons that that atom would have if it weren't part of the molecule, right? But that's the same thing. The group number, the number of valence electrons in a free atom, those are the same thing, right? Instead of thinking how many non-bonding electrons are there, you could think of this as how many lone pair electrons. So just make sure you're thinking about how many electrons and counting the electrons individually and not how many lone pairs, definitely how many lone pair electrons, right? And then instead of adding up all of the shared electrons and then doing division, which isn't that hard to do, you could instead just add up the number of covalent bonds. Okay, so this is way number 2 to think about it. Again, functionally equivalent. Number of valence electrons minus the number of electrons in lone pairs minus the number of covalent bonds. And then the last way to think about it that I'm aware of is the way that I learned it and the way that makes the most sense to me, probably because that's how I learned it. And that is to figure out what the valence is on the atom if it were free. So same, starting off the same. And then subtract the number of items or things associated with that atom. So now these are not technical chemistry terms, items and things. So I'm gonna need to point out what I mean about those. But what I mean is that each electron in a lone pair counts as its own thing, because the way we draw them in a Lewis structure is each as one dot. And then as long as you are drawing your Lewis structures with lines for bonds, which everyone should be doing by now, each line counts as a thing or an item. So let's go back to the last slide and apply this. Actually, we got to go back all the way over to here to apply this. So now look again at the oxygen of H3O plus. We already know the answer is +1, but let's apply the thing or item strategy. So oxygen would have 6 valence electrons if it were free, right? And it has right now 5 things around it. 1, 2, 3, 4, 5. So if you count each line of a bond as a thing and each electron as a thing, you can get 5 things, and then you just have to do 6 minus 5 is 1. And then you don't have to worry about all these multiple steps of math. Not that any of the steps are hard, but again, just whatever way works for you, whatever way makes the most sense to you. You can apply the same thing if there's multiple bonds. So let's look at nitrogen here. Again, nitrogen has a valence number of 5. And surrounding this particular nitrogen, there are 5 things. 1, 2, 3, 4, 5. So keep in mind we have a triple bond here, but each line of that triple bond counts as a thing. So we have a valence of 5 minus 5 things, which means we have a formal charge of 0. Does that make sense to you guys? Again, thank you. All 3 of these methods of approaching formal charge are correct. It doesn't matter which one you use. I'm not going to give you any of them on a test, so everyone can choose for themselves.
I have a question.
Yeah, please go ahead.
When you say subtract the number of items or things, we're not just subtracting the lines, we're subtracting like the lone like the electrons on the side, right?
Yeah, exactly. That was a good way to put it. Each electron of the lone pair counts as a thing. So every dot or line, right? Items and things in this case collectively means dots and lines. So if you count up how many dots and how many lines, that's how many things you have. Does that answer your question?
Yes, ma'am. Thank you.
You're welcome. Okay, so let's try it on another thing using another molecule using whatever method you want to use. I've put the 2 that are harder to remember for me, at least, up on the slide. If you're using the thing method, then hopefully you remember it already. So I want everyone to figure out on their own what the formal charge is on the nitrogen atom. And I've given you some multiple choice options over here on the side. But before you launch into your math, I want you all to take a moment and think about, do you have all of the lone pairs? Is it possible that there is a lone pair, that this is an incomplete Lewis structure, and that there's actually a lone pair on that nitrogen? Is that possible? No?
Oh.
Awesome. You guys don't even get tricked by my trick question. If you were to put a lone pair on that nitrogen, then you would break the octet rule with electrons, and you can't do that. So you have all of the electrons, and usually if I ask you guys to tell me the formal charge on a molecule on a test, I would say something like, the molecule below is showing all electrons, but no formal charges. What is the formal charge on blah 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 atom? Okay, so now knowing that, what is the formal charge, if any, on the nitrogen atom?
I only remember
Positive
the
one?
cycle count. +1, yeah, positive one.
I've had a couple people say +1 verbally, and a bunch of people are putting it in the chat box. That is right, but I think somebody might have had a question. I couldn't tell if that was a question or a hot mic. So if you had a question, will you please ask it again? No, okay, just a hot mic. Cool. All right, so the answer is indeed +1. There are 5 valence electrons for nitrogen. And if you're doing it my favorite way, then you can count 1, 2, 3, 4 items and you're done. 5 minus 4 is +1. If you're using either of these two formulas, then you can calculate so that you have 5 minus 4 covalent bonds minus 0 lone pair electrons. And then you're done. Okay, cool. So I want you guys on your own when you're reviewing the slides after class, because you should be reviewing the slides after class. I want you guys to take some time on your own and answer these questions about the same molecule. I'm going to move on for now. Okay, the last thing that I want to say about formal charges is that I want to kind of point out some patterns. Your book puts these in a chart, but I want to take a moment to talk about them because I think it'll help kind of solidify and bring everything together. And especially if you try this and practice it some, and then come back and look at this chart again, it'll solidify it even more. All right, so I put up 2 different examples of a bonded carbon atom up in the middle of the slide. The one on the left here is the type of one that we're most used to looking at. That's a carbon bonded to 4 things. I think I talked about this either Monday or Friday, but carbon really likes being bonded to 4 things. Or let me say more accurately, carbon really likes having 4 bonds around it. That can be 4 single bonds like I'm showing here, or 2 single and 1 double, or 1 single and 1 triple, but it likes to have 4 bonds. So that is a neutral carbon atom that's bonded to 4 things. It has a full octet because it's sharing 4 covalent bonds, which is 8 electrons. If we were to replace one of these bonds with a lone pair, so say we were to break this bond with whatever element it is that's over here and give both of those electrons to the carbon, we would get a Lewis structure, a partial Lewis structure that looks like this, where this carbon now has a lone pair in place of a bond. Now, when we did that, instead of 2 shared electrons at that position, now it has 2 electrons all to itself. So you can imagine that means that it's bringing more electrons towards itself and carrying them all on its own now. So now it's going to carry a negative formal charge. And if you go through the math, through whatever mechanism you want, then you'll see that this negative formal charge is fitting with our equation, right? So carbon has a valence of 4, and this has 1, 2, 3, 4, 5 things around it. And so 4 minus 5 is -1, all right? So what about the other way? If we take this not the lone pair, if we take this pair of electrons that's in this bond and give them away to whatever atom it was that was on the other side, well, what we're going to leave behind is a vacancy, right? What we're going to leave behind and what we're going to end up with is something that looks like this. We have a carbon bonded to 3 things. It only has 6 electrons, so it has not fulfilled its octet. It hasn't broken the octet rule, right? In order to break the octet rule, it means you have more than the octet, which we're going to not do in this course. But it doesn't have a complete octet. So it's still okay, because the octet rule, if you read it carefully, says that every atom wants to get a full valence shell, but can't get more than a full valence shell, right? So we haven't broken the octet, but we are electron deficient. We took our 2 shared electrons and gave them away. So now we have some positive charge build up on that carbon. And indeed, again, if we apply the formula, my favorite formula, then we have carbon with a valence of 4, and then we subtract 1, 2, 3 things from that. So 4 minus 3 is +1, and my lights went out again. So think about that for a minute. Okay. So hopefully this makes sense. Someone has asked in the chat box, is the formal charge of an overall neutral molecule always 0? So that's we're gonna get into some terminology for me to answer that question. Formal charges are associated with specific atoms within a molecule. So you can't actually ask about the formal charge of a molecule. You can ask about the overall charge of a molecule. But the word formal charge, the term formal charge, is associated just with a particular atom. Okay, so that being said, and I think I have a slide on this coming up, but just in case I don't, if you add up all of the formal charges in a molecule, it has to add up to the overall charge. So if you have a neutral molecule, then you have to be able to add up all of the formal charges in that molecule on those atoms, and they have to add up to 0. Or they could all be 0, because that'll still add up to 0. Someone said, so that's what it would look like if carbon did an electron transfer, which would be an ionic bond, but I thought carbon only makes covalent bonds. Okay, yes. There's very few times in organic chemistry or really in life that we can say always or never, and we're not gonna have any exceptions to that. So carbon very strongly prefers to make covalent bonds. There are gonna be exceptions. And just to point out, if carbon has this bond broken and doesn't keep those electrons, this carbon here on the left doesn't have any ionic bonds. I mean, I know it's an ion, so okay, maybe it would have an ionic bond. I'm walking myself into a little bit of a hole here, but I'll just stick with my original answer and say that carbon prefers to make covalent bonds. Okay, so just to finish off formal charges, because we gotta get going on to our next topic. This is the rest of that table. So this table in your book, table 1-1, shows you these patterns for a lot of the elements that we're gonna be playing with here in organic chemistry under common methods. And it tells you about how this is a very important table. And I'm gonna tell you, no, this is not a very important table. I don't want you guys to memorize this table. You can memorize this table, but I don't want you to, because if you think about how fast it is now that you guys can know the valence account 1, 2, 3, and 4, 5, and know that this is a neutral, no formal charge, you don't need to memorize this table, because that is brain space you can use to actually think about cooler stuff. So I don't want you to memorize this table. I want you to understand how to calculate formal charges. I want you to be as comfortable with the principles as you can, that you will be able to do it quickly and comfortably. And I promise you, you will be happier in the long run than if you memorize this table. So we want to think about why in this class and be able to understand the why and apply the why. Okay, that covers it for formal charges. I'm going to move on to resonance in the time that I have left. And you guys will begin to see how Lewis structures and formal charges come together in resonance land. And so let's first talk about what I mean by resonance. First of all, I want to point out a couple of things. In order to have a legitimate and complete Lewis structure, then we need to try to fulfill the octet rule for as many atoms as possible. In order to do that, in order to other elements of a full and complete Lewis structure, you need to make sure that you have the total number of electrons that were available to the system. So that means that we have the number of valence electrons that all of the atoms involved would bring in. And then also we account for whatever positive or negative overall charge is associated with the overall molecule. So we did some brain exercises at the beginning of class, and we'll do another one here. So thinking about this second bullet point here, we want to make sure we have the correct total number of valence electrons in the system, or the number of total electrons available for bonding and non-bonding electrons. So I want you guys to think about this molecule, NCO-, and answer for yourselves in your heads for just a moment, how many valence electrons are in the system overall? So valence electrons and in this molecule. So take a moment to think about that. And someone's asked about discussing multiple bonds. We did touch on that in a previous class, and we will talk about multiple bonds more. For the purposes of formal charge, each line of a multiple bond is a thing, and that's all kind of that you need to know for the moment. We'll get to more of that stuff. Okay, so how many valence electrons are in NCO minus? 16. All right, let's see if that works out. That sure does work out. So we got 5 from the nitrogen, 4 from the carbon, 6 from the oxygen. That would give us 15 if we add up that math. But the overall molecule is negative, so we have to toss one more electron in there to account for that overall negative charge. So we have 16 total electrons. Nice work. Okay, and then the final thing, as I mentioned in the last kind of set of slides from this class, the last thing we need to get a complete Lewis structure is to be sure that we're showing any and all formal charges. Okay, so now that we're sure about, we know how to draw complete and legitimate Lewis structures, I want to, this is my example here of NCO minus. This is one legitimate Lewis structure for NCO minus, and there are others that we will see. And the fact that you can draw more than one legitimate Lewis structure for a molecule, not every molecule, but some molecules, you can draw more than one legitimate Lewis structure, is what underlies the idea of resonance that we'll be talking about for most of the rest of class. Okay, so one more thing I want to mention here about legitimate and complete Lewis structures is that you guys have built-in ways to check your own work on this. So here's a couple of hints for you on that. After you go through one of the methods to create your Lewis structure and you have your total number of electrons, count up the total number of electrons you've drawn into your molecule and make sure that it matches the number of electrons that you expected from your original calculation. I can't tell you how many times people forget to draw in a lone pair, even though they know it should be there, but they just forget to draw it in, and then that's not a correct Lewis structure. Same thing with formal charges. Make sure that if you have formal charges that are supposed to be present on any of the atoms, that they are there. And then make sure also that if you add up all of the formal charges on each atom, they add up to the total overall charge of the molecule. Okay, on to resonance structures. What do we do if we can draw more than one legitimate Lewis structure for a compound? Well, we use them all. And so that's really the basis of resonance structures. Resonance forms, by definition, are Lewis structures for a molecule that can be interconverted by moving only electrons. That means you're not allowed to move the nuclei of the molecules. You can only move around the electrons. So let's see what I mean by that. Here is a Lewis structure of a particular molecule. And I'm going to tell you this is showing all of the electrons and all of the formal charges. Notice that we have not broken any octet rule here, so this is an allowable Lewis structure. There's another Lewis structure, though, another variation, where if we leave all of these nuclei in place, all the atoms in place, and this lone pair becomes flexible. So you can't really move around single bonds because single bonds are what keep the molecule together as a molecule. But we can move around lone pairs and we can move around the multiple portion of multiple bonds. You'll see that in a couple of slides. So we can take this lone pair and instead of having it isolated on nitrogen like a lone pair, we can move it to be shared between carbon and nitrogen. And when we do that, we get a different Lewis structure for the same molecule, excuse me. All right. A different resonance structure for the same molecule. A different Lewis structure for the same molecule. So these two are resonance forms of each other. And we as chemists, we denote that with this weirdo arrow here that has arrowheads on both sides of it, and also by these brackets. Well, what does this really mean? What it means is that the true structure, the real, remember, Lewis structures are tools so that we as chemists can imagine and communicate about where electrons live in a molecule or where they are in a molecule. So when we have more than one legitimate Lewis structure, what that tells us is that neither actually represents the truth about where electrons are in that molecule. And so the truth for this molecule is some kind of a hybrid. where there's some bond between the carbon and nitrogen that's not really a single bond and not really a double bond. And this formal charge doesn't really live only on the nitrogen or only on the carbon. It lives in one place or the other. So you can think about this as being an average of the two Lewis structures, or you can think about it as the two Lewis structures converting back and forth really fast so that it's so fast you can't see, and you see like a combination. I'm not going to ask you guys to draw these combined representation types of things, but I might ask you draw all of the valid Lewis structures for a particular molecule. And then I might ask you which one is the most important one. So we're going to talk about that for the rest of class, which one is the most important one and how do you know? So as I just alluded to, not every resonance structure for a compound is equal. Sometimes there's a Lewis structure that is more accurate for how to describe that compound than another. So the most important take-home major message here is that the major contributor is going to be one where all of the atoms have a complete octet. So I'm showing this example here of this molecule, which is called formaldehyde. You guys don't necessarily need to know that, but formaldehyde is a preserving agent. So we can take two of the electrons in this double bond. So we can make this double bond a single bond, and we can take two of these electrons and move them up to the oxygen to give us a lone pair on the oxygen. And when we do that, that'll create formal charges for us, a negative one on the oxygen, a positive one on the carbon. You guys can go through that math on your own. And we really do need both of these Lewis structures to describe formaldehyde accurately. But the one here on the left with all octets filled is much better at describing the molecule than the one over here on the right where the carbon does not have a full octet. And the hybrid version of this looks, again, closer to that one on the left, but demonstrates a dipole, a strong dipole of that carbonyl bond. So how did we know to put those two electrons from that double bond on the oxygen and not on the carbon? We could have done it to the carbon too, right? So we could have taken the two electrons here and moved them to the carbon. This would have been valid as well. It's just not a very good contributor. If we had done that, we would end up with a negative formal charge on the carbon and a positive formal charge on the oxygen. So now let's think about that for a couple minutes. Do you have a question? Okay, thanks. So you guys have seen this slide, or at least a similar one from our first couple of classes where we talked about the different kinds of bonds, right? And in a covalent bond that is polarized, those electrons are not shared evenly. They're going to tend to hang out closer to the more electronegative element, right? So the same thing is true when we're thinking about Lewis structures and resonance forms. If you're moving electrons around, those electrons are going to prefer to go towards the more electronegative element. So this is a picture, just a visual image of what that might look like in terms of electron density. I'm actually going to blow through this slide because it's more relevant to later chapters, but you guys can read through this stuff on your own. So I want to get to this slide, which really lays out the truth of it, that the more electronegative elements over here in the top right of the periodic table, they do a better job stabilizing that negative charge buildup. And the ones that are in the bottom left, the more electropositive elements, do a better job stabilizing positive charge buildup. So what that means is that if you have a formal charge, you want to put your negative formal charges on the atoms that are more electronegative, and positive formal charges on the atoms that are more electropositive when you have to make a decision. Okay, so these electronegativity trends are really important. They're going to be very fundamental for many, many, many aspects of the course. I have another couple of slides that I'm actually going to flip through really quickly right now to get to a key point slide, and that is this slide. When you show, and I'll go back, don't worry, I'll post those slides, but I'll spend some time on Friday on them. When you put resonance forms together and you're looking at different resonance forms and trying to decide how they're the most important, which ones are the most important, you're going to follow these rules in order. And as soon as you get to a rule that identifies the single most important resonance structure, you can stop and you don't have to go through the rest of the rules. We'll talk more about these rules on Friday. Really quick, just note that the last section that we were going to talk about today, chemical formulas, I wasn't going to say very much about it at all, except to say that there is a section on your book that goes through this. It is pretty straightforward, and so I'm not going to spend class time on it. I've made slides and I will post them with today's slide set, but you guys are responsible for reviewing these slides and this section of your book before Friday's class. And that's all I have for you guys today. So I can stick around briefly, like 1 or 2 minutes for questions, but otherwise you guys are free to go.
Thank you. Bye.
Thank
Thank you. Thank you. Thank you guys.
Thank you, Martha.
I have
I'll
a
see you
question
Friday.
on the book.